Can we call this the Glass-tastic episode?
Absolutely. The Glass-tastic voyage. All right. Yeah. We're
coming to you now.
Yeah. Coming to you. Okay, cool.
Perfect little intro.
Yeah. Hey, Sean, how's it going?
Oh, fantastic. Yeah.
Are you ready for our Glass-tastic voyage today?
Is that, yeah. Yes. Glass-tastic voyage.
I stole it from you. You came up with that one, but I've been saying it.
Yeah. Now, glass is such an interesting part of building science and facades and the space we work in.
Yeah.
And you can get really deep on the technology and the science behind it, materiality.
Absolutely. I also have gotten very negative feedback as a building enclosure engineer when I walk into a meeting and people are talking about windows, and I suggest, why don't we just not put any windows because it'll be a much more energy efficient, much easier to design, and we just put screens on the walls that look like windows, and you just project the outside onto that screen, you're good to go. And they don't usually like that. They still want a window for some reason. I'm not sure why.
Yeah, despite our best efforts, buildings will always have windows.
Yeah. Unfortunately.
Yeah, it's just part of the nature of the game, isn't it?
It is what it is. I remember when I was still working in Canada, I had this building that was about 25, 30 years old or something like that. And they were trying to change the glass from that very 1970s, 1980s kind of coppery gold tint on the outside, kind of like reflective coating, to something much more clear, because most modern buildings are using, much more clear glass with a coat, like a lowy coating instead of a tint.
Yeah.
And I went into like the documentation for, it must have been Saint-Gobain or like one of the big major glass manufacturers. And they had an infinite number of different glass makeups that have different, amount of visual light coming in, different amount of reflectivity on the inside or the outside, different amount of R value, different U value, different solar heat gain, different this, different that, different
Completely
colors. Yeah.
Picking a type of glass, like picking a paint.
Sure.
Like there's
different types of paint. There's different finishes on the paint, like matte or gloss. There's different thicknesses or all kinds of things.
But even like the color of red.
Sure.
So there's
infinite colors of reds. Red. Yeah.
Glass is exactly the same. You can make it do anything you want.
And it's also very subjective as well. The same way that paint is. Some people like green. Some people like red. Some people don't like a certain shade. And that's kind of the same thing with a window. Some people like a good reflective outside. Some people like a coppery look. Some people want it to be fully clear.
Yeah. Hot tip for any engineers out there. Early in your career, whether you are or not, claim you're colorblind. It has saved me so many times from choosing paint colors.
That's the tip.
It's such a great tip. Is I'm colorblind. I'm sorry.
I see. Okay.
And you just don't have to deal with that nonsense.
Wow. I go the opposite direction. I'm like fully into it and like talking about it with the architect and giving them samples and suggestions and stuff like that.
On the topic of colors, it's a bit not related to glass, but on the topic of colors, we were rehabbing and painting a building, 3 tall buildings, and picking the color to paint the buildings with 400 unit owners, massive drama. So we tried 2 or 3 different paint mock-ups on like we painted 2 full stories of the building.
Oh, wow. Big mock-ups.
The corners,
Sure.
2 stories of the corners,
to
see what it looked like, and that wasn't getting anywhere.
No agreement at all.
Well, I was like, we kind of like that, but we're not sure.
Sure.
So what we did is I don't think we changed his email title, but we introduced one of the guys in our office who's an architect as a color specialist.
Perfect.
And
nice.
And brought him to the site, and he said, that one's perfect. And they're like, yeah, we agreed. We like that one too. It was great. It was great. The buildings look great. The buildings look fantastic.
So here's a hot tip. Either pretend you're colorblind.
Yes.
Or pretend you're a color expert.
Yes.
And either way, people will trust you.
Yeah, not a color specialist.
Yeah.
Color expert.
Interesting, but we're not talking about paint. We're talking about glass. But the same kind of thing applies. Everyone has very different opinions about what they want to see through the glass.
And you see, it's not acoustics is really subjective.
Sure.
We'll do an episode on acoustics. Did a class on that in university. It's so subjective.
Sure.
And I've got real world experience with it as well. But I'm wondering if glass and eyesight and that sort of thing is as subjective as acoustics is. Like, when I look at a piece of low E glass next to clear, you can see it's a tint.
Yep.
But it's like 1-2% difference than clear. Like it's so
yeah.
minimal.
So what I've found, and this is what I like explain to architects, is like I'll bring two samples, and if you're looking at two samples side by side, you will absolutely see a difference. One is clear, one has like a weird reflection to it. And the reflection is either maybe a little bit purple, a little bit blue, a little bit green. But in certain angles in the light, you'll kind of see it. But if you have a whole building that is either clear glass and you walk in, it looks one way. You walk into a different building that has low E glass, you're probably not going to see a difference.
Yeah, two pieces side by side, you'll see a color difference. But some of the low E is so minor in the color distortion now that it's almost imperceivable.
Low E coatings are a coating on the glass. Now, if you have, let's say, an IGU, a double glazed unit, 2 panes of glass, that low E coating is going on one of those panes, the inside panes.
Yeah, so outside to inside, surface 1, 2, 3, then that's your inside pane. 1, 2, 3, 4.
And the coating is going
5, 6 if you have triple pane.
Sure, and the low E coating is going on either 2 or 3 on the inside of that glass.
Usually 2. Like
here in New Zealand,
cold climates 2.
Yeah, I found that some of them in Toronto would be on side 3, but there's like a negligible difference between the two.
It's like 10% difference between them.
Yeah.
And if you're optimizing buildings, and you may want to pick one or the other.
Exactly. But basically what the low E coating is a very, 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 very thin coating of metal. And basically they're getting the glass and they're spraying it with some sort of metal. I don't know how they do it. I assume they're not drinking it and spitting it on it. There's probably some sort of nozzle. Maybe it has something to do with that float glass. I heard you mention.
No, it's done afterwards, so it's
okay. So it's a separate thing.
The process.
If you know, tell us. But basically, it's a very thin layer of metal on that glass, and they change the proportions of what types of metal are in that coating.
It's so thin you can see through it.
Correct. And what that metal does is it acts like sunscreen, because sunscreen, like the old school sunscreen, has zinc in it, and that zinc reflects that UV light away from your skin. And that's basically the same thing that a low E coating does. So I just replaced my windows at my house and went with PVC windows, like the frame, but the glass, I used like a light low E coating on 2 of the windows. So like a 0.65 solar heat gain coefficient or G value. And then my 2 clerestory windows, the ones that are up high that are facing right, I believe they're facing like northeastish,
sun side.
right in the sun in the morning. Those ones I went with a stronger low E, which is like a 0.4, 0.35 SHGC. And so the ones with the weaker coating, I do not see the coating at all. The one with the stronger coating, if I'm looking from far away, and especially if I have polarized glasses on, you can see it. But if you're just kind of not really specifically staring at and squinting at it, you won't notice a thing.
It's that side by side thing. You might notice it, but otherwise, not even that you get used to it. Like you just can't. You can't see.
You can't perceive it.
So minor.
Because if you're not seeing the difference between it, you can't tell what's inside and outside. So
it's not tinted glass.
Correct. And like I've been in buildings, like older 1980s buildings that are tinted, they feel dark on the inside, whereas a low E coating glass building, you go in there and it feels pretty bright.
Yeah, it's interesting because the tinted glass will block the visible light, but not the
solar heat gain?
The
energy?
Gain. Yeah, the energy part. So
there's a somewhat correlation. Like usually tinted are usually blocking more of the sun out, but usually it's coming with the visual light. And so
like heavily tinted,
Yeah. If it's a very light tint, you're probably not getting much of the effectiveness of it, but you're still blocking some of the light.
Yeah, versus like the low E coatings. The variable of solar heat gain coefficient and visible light are almost independent now.
Yes, basically.
The technologies and coatings are so advanced that it's imperceivable. You can make it do whatever you want. Those 2 variables in particular are almost independent of each other.
Yeah.
The U value, I think, is more closely tied to the G value.
Sure.
Because the reason you're getting better performance out of the low E is from the emissivity.
Sure.
And a portion of that U value is emissivity.
Sure.
Coming across.
It sounds like we should probably define or explain how low E coatings work and what they are in terms of like comparison to tint.
I don't know how they work.
I know a little bit.
I know the surface level, but This is the thought experiment. Is if you drop someone in the forest, how long would it take you to send an email?
Sure.
If you gave me infinite resources, I could not figure out how to make a low E coating.
I could do it. I'm a professional.
How do you apply nanoparticles of gold to glass?
I would design nozzles of some sort. Yeah. Drink the titanium.
If you are a glass specialist, particularly in low E coatings, we'd love to talk to you about how the hell you develop them.
Yeah.
How do you apply them?
And how do you make them differ so like with such small differences, but there are overall they're big differences, but you can have ones that are so similar to each other but slightly different on those different values.
It's the whole world of nanotechnology I don't need to understand for my job.
Yeah.
But I'd love to know more about.
Absolutely, yeah. But in just as a general kind of overview, because we're not going to get into the nitty-gritty, you have tinted glass. That is basically the glass itself has some sort of coloring in it that makes it slightly darker, makes it more gray, makes it more brown, makes it more green, whatever tint color you want.
Just shittier quality.
Basically, yeah. You're putting what's it called? Basically impurities into the glass to make it a certain color.
Yeah, if you want ultra clear glass, you're going with low iron glass.
Correct.
Which is imperceivable difference in clarity, but it's a thing.
Yeah, it looks slightly less green than typical glass, or slightly less blue, maybe.
I don't think there's a cost difference whatsoever. Yeah. So if you're gonna design a really big glassy building, you have low iron glass.
Yeah, exactly. But anyway, so tint. You're basically messing with the actual glass itself, the chemistry of the glass, and changing the color. And that could block some of the sun in terms of the heat, but usually it's blocking the actual visible light and then maybe a little bit of heat as well. Which
can be important too.
Sure.
Like don't be around some tint next to like glare next to offices and desks. You may want to drop the visible light.
Yep, exactly. And it's also just, that's how things were done back in the day, 1970s, 1980s. That's all they had. Now with a low E coating, it does two functions. First of all, it cuts out that solar heat gain from coming into your house and warming things up too much. The stronger the G value, or the lower the number of the G value, the better it is at doing that. But it also blocks heat from escaping in the winter. So if you're heating your house, it also reflects that heat back inwards the same way it reflected the heat outwards during the summer. So
I hear the term reflection quite a bit. I don't think it's reflection.
Okay, what is it?
It's actually the emissivity changes.
Oh.
So radiation from this like third year mechanical engineering, right?
True. Yep.
Reflection is not really a thing. Reflecting heat is not necessarily a thing. It's that the shiny bodies don't emit the heat to other things. So if you've ever gone down like a shiny metal slide in the summer,
and burnt your ass on it,
they're crazy hot. They don't lose the heat.
Sure,
out, but reflect heat or not emit the heat is the more correct. Term of it. But.
Yep.
So the difference between surface 2 and 3.
Yeah.
I did a deep dive on this. I just remember I did a deep dive on this once. Trying to figure out what the difference is between being shiny coat facing air or shiny coat facing glass.
Sure.
That's the difference in your summer versus winter, or your surface 2 versus 3, is if the shiny side's facing the air gap, that is going to perform differently than the shiny side going to the air through the glass.
Sure.
That's the difference.
Yep. And so the common thing that I've heard, I'm not sure if it's the case for every single coating, but usually people will say put it on surface 2, which is on the interior face of the exterior pane, because that blocks more of the sun in the summer, and then surface 3 if you're less worried about that solar heat gain and more worried about heating in the winter, supposedly. But I'm sure there's probably variability between coatings and things.
From what I'm hearing in particularly the Vancouver market, Australia for sure, they've known about this for years, but New Zealand market now is suffering some of the consequences, is a lot of the insulation values in roofs and walls and window frame technology, etc., requires now, not mandated by code, but to prevent overheating. You have so much insulation that you have to have low E coatings to prevent overheating in Vancouver even.
Because the code and minimum insulation values have probably been guided by winter and heating as opposed to summer and cooling and keeping things from overheating.
There's some climate change effects for sure.
Sure.
I don't know exactly how much that's contributing.
Sure.
But definitely there are overheating problems in very cold climates now.
Yeah.
I'm even hearing like cold places like Prince George, BC,
Sure.
Calgary, like Edmonton, like places where they're notoriously cold climates. the insulation now has gotten so good that now you you're gonna have a great building in the winter, but you have that solar gain coming in. You need to stop that in the summer. So now you've
might be
almost reversed it.
Burning a whole bunch of energy on AC just to stay comfortable inside.
Well, here's now the argument is you look at buildings in Auckland, New Zealand being built, which is a cold climate. Make no mistake, Auckland is a heating dominated climate.
Yep.
Office buildings being air conditioned 10 months out of the year.
Yeah.
Because
they're all glass.
They're all glass and they're high G values.
Yep.
And they have not, they've been designed for winter conditions, not for the summer conditions.
Yeah. Yeah. We're going to probably see a lot of retrofits that have to try to sort that out, and they might be just swapping out the glass. That could be one way to do it. Could be increasing or changing out the HVAC in some way to try to, I don't know, mitigate something. But you want to stop the heat gain from happening first. Could be like external shutters. I've seen retrofits of older buildings where they put like a chainmail kind of thing in front of the glass.
Retrofitting glass sucks.
Yeah.
I'm only aware of one for sure. Maybe get to 3 or 4 buildings globally which have replaced glass.
Okay.
One was the One Wall Center in Vancouver.
Sure.
That's got an entire podcast episode about that building, which would be awesome if Peter Wall's listening.
Yeah. Come on down.
Yeah. That's got an incredible, that could be a mini series in itself.
Sure.
The other one was the one in London that was the concave one that was...
The one that looks like a cell phone?
No, the one that was melting cars.
Yeah. I think it looks kind of like an Ericsson.
Glass out of it?
Maybe? Probably?
It was like a death ray. They must have replaced it.
I mean, if
you're in London area and you know about that project, drop in the comments what happened with that building. It was burning people. Like, it was pretty serious.
Yeah.
I just don't know if it's been replaced or not, but you'd replace glass for that reason.
One would imagine. I've had ones where they replace glass, but it's usually in addition to the rest of the cladding and the rest of, like, it's a full retrofit as opposed to just the glass itself. Yeah.
We swapped glass out on a project in Auckland. Office building, 3-story building, all curtain wall around it.
Sure.
And just didn't have the money to do a full retrofit of all the curtain wall.
Sure.
But it needed a refresh. It was like a 1960s or 70s kind of curtain wall. It was pretty tired looking.
Sure.
And what we did is we brought in new curtain wall on the front facing part of the building.
Okay.
And back around the corners. So from the front, it looks like a brand new building.
Sure.
And then we just swapped the glass on the rest of the building so that it blended.
Cool.
And great result. It's actually right by the highway in Newmarket area.
Okay, cool.
One of the first jobs we worked on, actually.
Interesting.
I think I designed it at my old firm, and then we did the monitoring at Oculus.
Really? Interesting.
Because the continuity is easier for us to take over the CM side.
Sure. Interesting.
Yeah.
Okay, so we talked about coatings a little bit. We'll probably circle back to it eventually. But let's talk about, like, the glass itself, the IGUs, how that all works. I remember it was probably 3 or 4 years ago, you walked into the office and you had this little cylinder and like a box of dry ice and a thing to test IGUs and the condensation risk within the IGU.
Yeah, where did that go?
I don't know. It's somewhere. It's probably in our equipment room downstairs somewhere.
I'm not even sure where we got it from.
I don't know.
But it's a frost point tester.
Yeah, because basically
I've got a story about frost point testers.
Do you? Okay.
Do I? Yeah.
Let's explain what an IGU is first.
Yeah.
You explained it on one of your explainer videos before, but just as a quick overview, you have 2 panes of glass. You have a separation, a spacer between that. That can be plastic or aluminum. The whole thing is sealed all the way around. And the interior air between those 2 panes is meant to be quite dry. There's a desiccant inside that spacer to make sure it stays dry. And the reason it's dry is so that at whatever temperature this building experiences, you're never going to have condensation between those two panes. Yeah. That's basically kind of how it works. The glass itself can change, the coatings can change, but that's basically how any double or triple glazing or quadruple glazing works.
Yeah.
What's the story?
So when you get the failure mode of IGUs is the outside seals break down and air gets in between the panes of glass. Now, if just a little bit of air and there's enough desiccant, it can sort of dry out that space and you don't have any real problems.
Yep.
But if you've got too much moisture between the panes of glass, you get fogging, and the fogging can result in a couple different failure modes. I've got 2 stories, actually.
Okay.
The one you see in cold climates is when the outside gets cold, you now get condensation inside your IGU, and you can't wipe it down because you can't get inside the glass.
And even if you wipe the outside, you're still not getting it because it's between the two panes.
Between surface 2 and 3.
Yeah.
So IGU fogging on the cold side is your common failure mode, and you can't do anything about it. All you can do is replace the glass.
Yeah.
So if you want to know how much moisture is in that space, or if you want to know kind of at what temperatures you would see that fogging, what you do is you take a cold piece of metal and you locally cool the glass down, and you measure the temperature, and whatever the temperature is where the fog forms, that's your fog point, I think, your failure point, whatever it's a specific name for it.
Yeah.
And so you can go around and you can get a sense of the quality of the IGUs in a new build. Were they all sent to site in good quality? Were they dry inside? You can also get a sense of how they're aging over, 5, 10 years, 15 years, whatever. And you can take a sampling of a selection of IGUs to get a sense of what was the overall quality of this build. To
just interrupt for a second, with an IGU, generally, you're getting that full pane. It has the desiccant in it. And the idea is that it's meant to last about 25 to 30 years. And what happens is that you have all these panes of glass around your building. And at that 25 to 30 year mark, you'll start to see a few per year that start to fog up because, they've been slightly air leaky. The desiccant has been used up, and then, they're no longer functioning.
Yeah, you get some statistical probability of failure modes.
Sometimes it'll last 50 years, but
if you got a brand new IGU, it'd be like minus 40 in terms of like the dew point.
Sure.
And at failure, when you start to see problems in Vancouver, you'd be like, if you're getting minus 10 in IGU, that's sort of an outside temperature that you'd start to potentially see those. So,
sure.
So that's all good. You could take a random sampling of pieces of glass to sort of get a sense. Or if you're involved in the litigation project, you can actually go measure every single IGU in 3 buildings, which I did.
How long did that take? Weeks? Sounds like a lot.
It was.
And a lot of dry ice.
3 weeks.
Sure.
3 weeks for 2 of us.
Sure.
Knock, knock, knock on the door. Walk in. You've got an elevation of the building. You've got your frost point tester. And your test every IGU, which is like...
And write down on your little piece of paper. Fair.
Write down your piece of paper. Go back, make a color-coded map of the elevations of each building. These are green, these are yellow, these are red. Present that to the defendants, settled weeks later.
Sure. Yeah. That's all there is to it.
How the hell did you do this? Like, we knocked on every door, went into every single one.
Checked all of the glass.
For failures and frost points.
And the thing is, like, they didn't need to do that because they could have just said, we need to replace some glass. But because it's a litigation, because they're trying to argue and try to point blame, and that's when you start to really dig into that
Actually,
rabbit hole.
We weren't frost pointing every single IGU. We were looking for defects in every piece of glass.
Fair.
But frost pointed at least one per unit kind of thing.
Interesting. Yeah. Okay, cool. So there's that. Let's talk about the glass itself.
The other failure mode of fogging.
Oh, sorry.
There's so the one is just seeing the condensation.
Sure.
You can't see through condensation.
Yep.
The other failure mode, though, is if that condensation is reacting with a low E coating.
Oh.
It can corrode the coating.
True. I have seen that before. Yeah, it starts to look kind of weird colors and stuff like that.
Yeah, it goes kind of foggy, milky colors.
Sure,
so,
yeah.
If you look up the One Wall Center in Vancouver, that's what happened to that building.
Interesting.
That IGU makeup is a whole story in itself, and others would probably tell the story better than I can. But the fogging was the problem. I've got a beautiful picture I took. So this is during the investigation. I was at a building like kind of a few blocks away, and it was a cold, clear morning.
Sure.
And I woke up and took a look, and you can see all these fogged up panes of glass, and it's like click, and like that's the report cover. I wasn't working on the project, but I knew it was happening. Yeah, it was just perfect.
Interesting.
Yeah, it's a whole cool case story, but that's another way that IGUs can fail.
Yeah. Other ways that I've seen failure are spontaneous breakages. Due to like inclusions, nickel inclusions and things like that. Yeah. Usually is that for like tempered glass, heat strengthened glass usually is the problem, whereas annealed doesn't really usually have that problem because it's not sitting under tension or compression.
Yeah. Just to finish off the IGU failures, corrosion around perimeter is the other spot that can cause problems.
Because the spacer corroding.
spacer or the sealants or some sort of chemical got mixed in during IGU manufacturing.
Okay.
Reacts with the coatings and can corrode.
Interesting.
I investigated that one too. So.
Interesting.
But back to your point about
spontaneous breakage.
So this is the glass itself, materials, toughened glass.
Yeah.
Toughened glass. The spontaneous breakage mechanism is called nickel sulfide inclusions. And if you Google that, you'll find out some cool stuff about really geeky glass stuff.
Yeah.
But essentially, it's an impurity in the glass, microscopic, but very tiny. You can see it with a naked eye.
Sure.
You see it with a magnifying glass or a high-powered lens. But very tiny, almost imperceptible to see. But the issue is that it grows in size, in volume. So if you've got it inside, it doesn't happen in annealed glass, like float glass, regular glass. It's all the same thing. Because it doesn't have the same stress concentration inside the glass to start with.
Sure.
But when you toughen glass, you create these compressive forces on the outside. You induce like this analogy I gave is like if you've got a rope, you hold it loosely, it doesn't have any tension in this direction. When you pull it taut, it's
much stronger.
But then when that loose piece of rope snaps, it doesn't really do much. But when you have a really taut piece, it'll snap, right? So in those toughened glass, when that nickel sulfide inclusion grows in size, it basically creates this spontaneous stress around it. And then suddenly, randomly, for no other reason, it'll just pop when they snap.
Yeah.
And you'll see a piece of glass will just explode.
You'll see, like, if it's a laminated glass that has it all held together, you'll see like this is a little dot and then all of the spider cracking comes out from that little dot, which is kind of interesting.
I would say in my career, I've seen 50 examples of nickel sulfide inclusions not related to projects.
Yeah.
Just walking by random storefronts, whatever.
I've seen those in Toronto. They had this a bunch of buildings that went up, and the balustrades were glass, and those were shattering due to nickel. Yeah. And they wrapped a couple buildings in mesh. Like they just had just wrapped the whole thing. Yeah, they didn't know what to do with it.
So if you're ever walking by storefront, piece of glass, whatever, and it's like a spidery crack, small little bits of glass, like yay size. There's actually the standard has the maximum size each piece can be. That's to qualify that your toughened glass factory could make toughened glass.
Oh, interesting. Okay, cool.
So you take a piece of glass, you smash it, and you count the number of pieces.
Sure.
If you ever see that walking by, you can look for the nickel sulfide inclusion. This is something that only building science geeks do.
Yep.
I do it every single time. So
same.
If you imagine there's a little microscopic point, when that piece explodes, it creates these two pieces called the butterfly, which is perfect match next to each other. And then all the breakage happens from that. So if you look close enough at the pattern, you'll find this little butterfly spot. And if you look really closely, you can actually usually see the defect in the middle of that.
Yep.
It's pretty cool.
It is.
And very few people know what the fuck they're looking at. But
yeah. I mean,
my wife looks at me like I'm an absolute maniac. Like, you looking at this broken glass. So I'm like,
I mean, like I do that with a lot of nerdy things. Like when I did a survey course when I was in university, and now every time I'm walking on the street, I see the survey points in the sidewalks and stuff like that. Yeah. Also, bubbles on paint. I notice those on buildings all the time, and I like to poke them. It's kind of fun to see the water come out. But anyways, back to the glass. So spontaneous breakage is one thing, but let's talk about the different types of glass. We have the annealed float regular glass. That's just basically glass.
I'd love to go see the process of this, but there's very few factories in the world that make float glass now. But you've got a bed of molten tin and you pour glass on top of it. Like,
molten glass.
How do you even come up with that as an idea? Like,
right? Like the first person to do that? But they basically float it on top of this really still thing, and it makes a nice flat piece of glass. Yeah. And that's just regular annealed glass. Which
I can just imagine the tolerances in like the vibration isolation from the
True. Also, airflow would have an effect if there's too much airflow.
All that stuff, I'm sure goes into it, or I'm sure it doesn't matter. One of the two, but
maybe it's heavy enough material that it stays flat. Doesn't really get affected.
To know what goes into that. If you design float glass factories, you give us a call.
Even if you've just seen a float glass factory and you've asked the right questions, let us know. But okay, so float glass, which is regular annealed glass. Then you have like a heat strengthened glass. a tempered glass. What's the difference? Like, what's the difference between heat strengthened, tempered, heat soaked?
Yeah, so annealed glass is coming right off the float factory.
Yeah, just regular
nothing
glass.
special to it. Regular old glass.
Yeah,
it breaks, it cuts you. It's pretty strong, but
yeah,
brittle too. You want to make that stronger, then you heat strengthen it. That gives you some strength, and I think the difference in strength is where heat strengthened versus toughened comes in.
Yeah, and toughened and tempered are basically the same?
I believe so, yeah.
Okay, cool, yeah.
And they'll have different standards on what classifies as heat strengthened versus tempered.
Sure.
One of them is breaking it and counting the pieces.
Sure.
One of them is the strength of the glass, and like there's a whole standard on qualifying your factory as toughened.
Yeah.
That nickel sulfide inclusion as well, if you're worried about that spontaneous fractures, you can do what's called heat soak testing. What that does is take that potential nickel sulfide inclusion and accelerates the growth of that. So if you're going to get a failure, you get it in a factory setting.
And then they send the right number of panes to site, and you don't have to worry about it shattering and then replacing.
Yeah, you can specify heat soak testing.
Yeah. I've personally not gotten it on any of my projects. Usually they'll ask and I'll say, here's the risk. Do you want to take that risk? And they usually do take that risk.
Doesn't reduce the risk that much.
Really?
Well, it doesn't reduce to zero.
Sure, of course not.
Even with heat soak testing, the rate of failure is like 3 in 1,000 panes of glass you'd expect.
Okay.
Whereas if you didn't do the heat soak testing, you could have, I don't know what the number is, but
5 or 6 maybe
per 1,000.
Yeah. Okay.
You might get into like that case in Ontario. I think it was like a lot.
That might have been a systemic issue with what they were doing to manufacture the glass, I assume.
Well, a lot of this spontaneous stuff comes from that, right? It's a defect. Yeah. It's an impurity in the glass. Yeah. So, you can specify heat soak testing. I don't know how you police it. Like, how would you know if it's been heat soak tested or not? You're just getting charged money to. I'm not saying
there might be a certificate.
I'm not saying that everyone does that, but I'm sure it happens. Oh yeah, no, we heat soak tested it for sure.
Yeah. Who knows?
Yeah, I've never asked for QA records. Maybe I should ask for it, but
yeah, slowly but surely we ask for QA records on things. But anyways, okay. So we have regular annealed glass, we have toughened, we have heat strengthened. What about what's it called? Laminated glass.
Yeah, laminates are pretty interesting. You can so if you wanted, they do some properties for you, some things that monolithic glass couldn't do or toughened glass.
Sure.
The biggest one's acoustics.
Sure.
The acoustic properties you can get with an interlayer. So a laminated piece of glass, you take 2 pieces of glass and you put a layer in between and you melt them together, so it creates this kind of sandwich, this delicious glass sandwich. And that inner layer can prevent some of the vibration of the outside to getting into the inside. And so if you have a 8.38 is a common kind of size of glass, that'll perform acoustically better than a 9 mil monolithic.
It's 2.44 millimeter
with a 0.38
inside.
Interlayer, yeah. And there's different types of interlayers that you can get in there.
You can get bulletproof ones if you really wanted to.
Yeah.
You can get security ones. Some of them are just to hold the glass together if it shatters, so it doesn't fall out. So for things like balustrades, generally, almost all the time, they have to be laminated, just because people could have glass falling on top of them. But you could be designing that just for strength. So if you have a really big pane of glass and there's a chance of people smashing into it, like bumping into it or whatever, sometimes that pushes you into the laminated because, one pane of tempered, toughened, whatever is just not quite strong enough. So you need the extra thickness and the extra flexibility from the interlayer.
Yeah.
So, yeah.
Yeah, it's a whole thing in itself. But, commonly done. It can do some cool things for you if you need to.
Yeah.
Like stopping bullets.
Sure. Yeah. Stopping bullets, stopping people breaking in. Like you have a big glass facade and you don't want people breaking in. That's another way to do it.
Yeah.
I've also, as a complete aside, I had this older building that was built in 1904. It was like a big old building on my university campus. There was a skylight, external skylight, and an internal ceiling light. And we had to kind of fix both because the external skylight was starting to leak. Wood was kind of rotting out and falling down onto the internal light. And so we had to figure out what to do. The easy one was external skylight, just replace that, double glazed, make sure it's, going to be nice and dry and nice and warm. But then the interior one, because it's a heritage building, we had to basically keep it the exact same. A little bit worried to replace all the glass because it's aged glass. It was like lead caming between the glass, like almost like what's it called? Stained glass, but all clear. Well, frosted, I guess. But what we were considering, and I left Canada before we finished this project, we were considering putting like that same type of security layer, adhering it to all of the existing glass and kind of adhering it also to the caming and also to the framing. Not sure where they ever got with that. Because we were suggesting, why don't we just replace all the glass? And the heritage architect was saying no. And so I wonder whatever happened with that. But there are options for retrofitting security membranes and things like that onto existing glass as well.
Yeah, we've got 2 heritage stories about glass too. So it's similar in the stained glass.
Sure.
We did a project in Seattle, St. Demetrius Church. Had see a picture of it. You could look up a picture of it on Google. St. Demetrius Church in what's that neighborhood called? It's down near University of Washington. But it's got basically a big dome complex and a big spire at the top, and this top's got this painted glass like all around. And a lot of the glass had failed. Okay. But we ordered like artisan glass, like handmade glass to replace it.
Because it has to have that waviness to it. It has to have a certain kind of color to it, maybe?
Well, like you could definitely not put clear glass back in there.
Of course, yeah.
But it was like we weren't replacing all the panes at the time. I think they maybe replaced the rest of them because they saw it was kind of colored glass to start with. Sure. And what they were able to get was sort of like a blended painted kind of artistic. I'm sure we'll put a picture up maybe. Sure. Of it. But yeah, it was really cool. They saw the replacement. They thought it was so cool. They replaced the rest of them, I'm pretty sure.
Interesting.
That was really neat. Yeah. Process. Fun. And also in Seattle, one of the coolest projects I'll probably ever work on in my life was restoration of it's an apartment that used to be a high school. Okay. Queen Anne High School. Look that one up as well. It's high school was built in like 1914. Sure. Like old masonry.
Yeah. Arches and things like that.
Oh,
probably.
Yeah. You even
gargoyles maybe.
Propose that shit now and you get shot down pretty quick. Of
course.
Although the U.S. just passed a law that said all government buildings need to have architectural
I would love to see how that actually plays out.
It'll be cool. Someone will figure it out. Yeah. Anyways, some of the windows were 100 years old, so they're being replaced, and so we had this company, Legacy Construction in Tacoma, that specialized in retrofitting heritage wood glass windows. Okay. So they manufacture new replicas of the old ones. Okay. And heritage listed buildings had to maintain all this stuff. Of course. They were taking the sash out of the opening, take it back to the factory, basically pull it all apart, replace all the putties, repaint the whole thing, everything. Sure. And so some of the panes of glass had to be replaced. And so you had these brand new pieces of float glass next to the original plate glass.
Which has waviness to it.
It has slightly. Slight variation to it.
Yeah. And it looks different.
If everything was the same, you would never notice.
Sure. But
next to each other, it's
glaring.
Stark. Yeah, it's a stark difference. Right? That's a replacement. So they had to sort plate glass. So we had to source plate glass for those paints.
People still make it? I guess certain people do it. Interesting.
I think plate glass is something you can do in your garage.
Sure. Just melt down some sand and pour it onto your metal plate.
Here's something I don't understand about glass. It's how you take sand, melt it together, it turns clear. I don't understand it.
If you know how that happens, please explain it to us.
I don't need to know it for my job. But
just curious. I mean, I guess maybe it's the silica. Maybe the opaque stuff burns off when you melt it or something like that. And it's only the silica that comes through.
Maybe glass point people would know how it works. But
maybe.
In that particular instance, the plate glass that was manufactured like replica. They had to I think you have to make purposely distorted glass to make it.
Fun fact, there's a third way to make glass that I've seen. I saw some videos probably on TikTok, but have you ever seen in the UK, certain pubs will have, plate glass as their windows, and one of the panes of glass will have this circular kind of ripple effect on it?
Mm.
You never seen this before?
No.
So I was in the UK and I saw a couple pubs that had that. Then I started going down a rabbit hole to look at that. And what it is the way that they used to make glass was they would blow the glass.
Mm-hmm.
And so you'd have your big glob of glass on the edge of your rod, kind of blow it out a little bit, and then spin so that it turns into a big circle.
Mm-hmm.
And the place where your rod was connected is that circular ripple effect thing. Everything else is much more smooth except for that one piece. And so pubs, when they were replacing their windows, would be like, oh, we don't mind the this piece because that's the cheap piece because everyone else wants the clear pieces. And apparently they would put that in there. And that's how things were done. So yeah, I was in Yorkshire and I saw this old pub that had one of those. And I'm like, what is that? And went down a rabbit hole.
Wow.
Interesting, right?
Yeah.
Yeah.
Yeah. The whole world of glass is very interesting. They love it. Float glass must not be that old then.
I guess. Yeah, I don't know.
Because like I'm talking like Queen Anne High School is 1914.
Yeah.
Certainly like 1940s and 50s buildings you expect to have.
Yeah.
Expect to have
some waviness? Yeah, absolutely. Although I feel like I heard something like years and years ago that glass technically isn't a solid. It's more of a liquid.
Yes.
And so it will migrate over time, supposedly.
Yes.
But is the waviness because of the migration over time or because it's plate glass or the spinny glass as opposed to float glass?
I think it's the flatness of the original design. Because what I understand is
Yeah.
plate glass, you actually have to grind it to make it smooth enough.
As smooth as you can, but there's still going to be variations.
Yeah.
Interesting. If you know more, let us know.
I'm sure. I'd love to have multiple people on about glass.
Yeah. We're just speculating at this point. We only know us.
It's also like the stuff we work on. It's like you never get into that nitty gritty of the technology behind or the.
Especially when you're working on a project, it's just like go, get this thing done, get it designed.
Now, when you get into failure investigations, then you start to get deep dive into it.
Sure.
So I've done a bunch of those, and you start to then find the research papers. What other failures seem like this? You start to understand the failure mechanisms. And
sure. Compare and contrast and see if it makes sense on your thing.
Yeah, come up with a reasonable hypothesis, test the hypothesis, prove that if you did this, this wouldn't happen. If you did this happened. That's why it looks like this. That's just really cool.
That being said, if you have any investigation stuff and you want us to work on it, let us know. Because that's what I get jazzed up about, doing an investigation on an old building and trying to retrofit it or solve a problem. New buildings are like, they're cool and stuff, but, it's not as interesting.
I like doing investigation work, except I don't like when buildings go wrong.
Sure.
It's almost like a bittersweet. Like you get to do some really deep dives on some things and some failure modes, and usually a lot of the stuff you've learned before is applicable to a new thing, and you can solve it pretty quickly. But you never want to see a building fail for any reason.
Yeah. And I mean, like, yes, you're there to fix it, but it also starts to make you worry, like, oh, are there similar things that have been done elsewhere? And we're going to see this as a systemic problem that we have to fix all these buildings, or is it just this one thing?
The investigations the reason I like investigation and forensic work is being able to think outside the box on how else we could fix this other than replace.
Sure. Yes, I also like that.
You don't even need an expert to say, just replace everything.
Burn the building down and start again.
Yeah.
Take it all down from scratch, do it again.
If someone's done an investigation, told you that's the answer, you get your money back.
Yeah.
Because you already knew that.
Yeah. Why would they even be there?
My 4-year-old could have told you that if something's broken, fix it.
Yeah.
Where you need an expert with that understands the things is, okay, what else could you do?
Can we keep some of the timber? Can we keep some of the window frames in place? Can we fix this thing by cleaning it a certain way and sealing it afterwards?
Yeah, fixing glass is going to be a tough one.
Sure.
For a lot of cases, bad example. But investigations in general, can you do something to get you some longer life? Do you need something to reverse the problem? How else could you make it go away?
Yeah.
Other than replace. That's pretty easy.
Yeah.
Thanks.
All that being said, let's wrap it back up to glass again. So we learned about the different types of glass, different coatings on the glass, the way that they go in, the failure modes and things like that. But if you have any other questions, concerns, weird projects that came up that you need to choose a glass, then
drop in the comments below if you've got some cool glass stories. We'd love to get links to research studies.
Absolutely.
Case studies, white papers, anything that is firsthand, this is how we learned about this, or I learned that.
First principle stuff.
That stuff in the comments is going to really help this podcast get to the next level of bringing in
depth.
Other experts. These first ones are going to be pretty high level stuff, but we really want to get to the nitty gritty of like, let's do a podcast on nickel sulfide inclusions.
Yeah.
As a
longer we go, the deeper we go.
Yeah, and so if you think you know the most out there about nickel sulfide inclusions, drop us in the comments or contact us otherwise.
Come prove it.
Yeah. Come tell everyone else about it. That's the whole point of this podcast, is to share lessons learned so that we can move this thing forward.
Yeah.
Across the globe, not just New Zealand and Canada where we work, but everywhere.
And we all work together to learn more. Awesome. Well, thanks, and we'll see you again next time.